My name is Brandon Nelms. I'm an application engineer based out of our Indianapolis office, and appreciate everybody coming here today. We've got a great presentation here for you. We're going to go through Evaluate. It's the whole reason we assemble. In 2009, renowned leadership expert and author Simon Sinek gave one of the most viewed TED Talks of all time, where he explained how companies and leaders achieve success and defy odds with a simple model he calls the Golden Circle. According to Sinek, average companies and average people go from what to how to why, and very few even get to why. But truly great and extraordinary start with why, then go to how, and last to what. And I thought that was a perfect model for explaining the evaluation toolbar tools, because if you ask me what the tools do, the answer isn't very exciting. But instead, if we ask why should we use these tools, we're going to see that the insight they provide can mean everything to us. So starting with interference detection, if we're worried about how parts fit together, or working on a massive assembly and we need to see if they occupy the same space, we can use interference detection. So how do we use interference detection? Simply select the assembly or parts we want to check. Then we can choose if there are components to exclude. How do we want to handle coincidence or subassemblies? And we could even group fasteners together, because it's okay to use a nut that doesn't have any threading on it. Then we select Calculate, and SOLIDWORKS takes over, showing how many interferences we have and what their volume is. There's even a visual representation of the interfering region on the parts. And if we expand the interferences, we can see what specific parts are interfering with one another. So we know the problem here is isolated to our base assembly. So let's go ahead and open that up and investigate a little further. There's a dimension on this tab that we can control to remove the interference, and then we can rerun our interference evaluation to see if we've taken care of our problem. So what does the interference detection actually do to our model? Nothing. But it does show us interferences. So as designers, we can evaluate whether or not those interferences matter to us, and it can provide that information in an easy-to-use visual representation. So next, why should we care about clearance verification? Some of you may design electronic components that need appropriate spacing for discharge purposes. Or maybe you need to be sure that there's sufficient space for lubrication to fit between components. So now our EE Sparky tells me we got to pay attention to the clearances on our batteries in our holder. So simply hiding away parts that we don't want to use will make this a much easier task. When we select clearance verification, we can select the parts or faces that we care to check. And then we specify what our minimum acceptable clearance is. And in this case, 0.25 millimeters. And then select Calculate, and SOLIDWORKS tells us that we have two parts that are at 0 millimeters clearance, so they're coincident there. And the results box shows us that both batteries are touching the outside walls. So for our design, that's okay at this point. We can always check in our options to see if we missed an option, but it looks like right now everything was right for our review. And we're really not worried whether or not the batteries touch the sides of the holder, but we do care about the spacing between the batteries themselves. And when we check the clearance between these parts and click Calculate, we see no clearance. Really what that means is there's no clearance problems. The parts in this case are further than our 0.25 millimeter requirement. And if that minimum requirement was changed to like 0.5 millimeters, you see we get a warning that the parts are inside that minimum acceptable clearance requirement. Fun little pro tip for you is that if you change the minimum acceptable clearance to 0, the output's going to be whatever the clearance is between those two parts, regardless of what that value is. So you can see we've got our coincident, our 0.44, and our coincident when we use 3 components. So what does clearance verification actually do to our model? Nothing. But we can check the clearance between specific components, and we can identify specific clearances that don't meet our specified requirements. So why should we care about hole alignment? This one's pretty obvious. Can I put my assembly together? I don't know about you guys, but if you've ever had a situation where you try and force a bolt through a misaligned hole, that's always kind of fun, right? A certain application engineer may or may not have stripped the threading on a bolt, making it next to impossible to get washers and nuts together at 2 a.m. on a Christmas Eve. So how would we solve that problem? We're going to use the hole alignment tool. We start by choosing a value for the deviation range. Here the default's 10 millimeters, which is a good starting point. And then we select Calculate. And you can see we've got several deviations listed. If we tighten the hole center deviation, the hole alignment analysis finds no errors. And if we use a hole center deviation that's too large, SOLIDWORKS won't correctly find the holes that we're looking for. It's really a value that you have to refine for your application, but usually the default works well. And if we look at a front view here, we can see the deviation in the holes. So clearly this wouldn't work for our application. And we would have problems obviously getting that bolt through. And then after we've fixed the problem, we can come back and double check. So what does the hole alignment tool actually do to our model? Get ready for this over and over again, and that is nothing. But we can check for misaligned holes, and then an unnamed manufacturer would probably actually have a customer still after my Christmas Eve endeavor. So why should we care about measure? Maybe we need to know the specific size of a part to ensure we're working on the right version. Or what about just checking a measurement to see the measurement of a result from multiple features? Now the measure tool is awesome. It's like having a tape measure to interrogate dimensions of your model. Maybe we want to look at the distance between some holes. Simply selecting the faces and we get an output to show distance, delta in the X, Y, and Z, area. And we can even dictate what type of cylindrical dimension we want to measure. Center to center, min, max, or some kind of custom distance if we care. Changing that dimension is available in multiple places here. And since I don't know the obviously mathematically superior metric system, I can switch over to inches so that the measurement number is actually something that makes sense to me, even though the template was in metric. We can measure across parts or hide parts to select other geometry if we want. And all the while, we're not modifying our assembly or running the risk of changing a part by editing a dimension we don't intend to. So what does the measure tool actually do to our model? Nothing. But we can measure distances, angles, and radii in sketches, parts, and assemblies and drawings. And we could do so between all types of geometric elements. Why should we care about mass properties? Maybe pre-printing shipping labels require a known weight, or we want to use mass for a rough cost calculation. And, it'd be pretty embarrassing if we got the final stages of manufacturing and our part actually won't fit inside an existing tool or anodizing tank. So for our assembly, let's take a look at the mass. In doing so, we can see the mass of this is 449 kilograms, which I think is probably pretty heavy for a flashlight, handheld flashlight. And since I don't know this metric stuff, I'm going to go switch the units. I don't think it's right, but let's switch it to pounds and see what happens. And I was pretty much spot on because it's nearly 1,000 pounds for a flashlight, so I think that's probably a tad high. But in looking at my assembly, I see the center of mass is precariously high. We can see in the graphics where that center of mass is up at the top there, which doesn't seem to make intuitive sense. So let's take a look at this switch part. And when I open it up, I can see there's no material applied. So what happened here is something I've seen several companies do that I think is pretty sneaky. In the document templates, they've set their default density to a high density to be sure that they change the material. So here we've got 1,000 grams per millimeter cubed. In any case where a material isn't applied, it applies this heavy material density, and that way we can always catch those situations. So we need to set the material to a plastic. Simply right-clicking on material and editing it, picking a plastic. We can switch back over to our assembly and rerun our mass properties analysis to see what our overall mass is, and that feels a lot better. So what does the mass properties actually do to our model? Nothing. But we can find the mass, density, or volume of one or more components or bodies. So why should I care about section properties? Maybe I don't want to do a full-blown sim analysis, but I do need to do a quick hand calculation. But where am I going to find moment of inertia data for specific faces? With section properties, I can select one or more faces. And by selecting Recalculate, I'm given not only the surface area, but corresponding moments of inertia as well. What I think is cool about this tool is you can also use it as results from section cuts as well. So here we haven't necessarily even cut the part, we've just done a section cut, and I get all of that data as well. So what section properties actually do to our model? Nothing. But if we need to find moments of inertia for sections, section properties can give us that information. So why should we care about sensors? Well, I know we all have a lot on our plate, and it's impossible to remember every little detail that you have to check off of the top of our heads. Or maybe we may even know some important design characteristic that other team members that pick up our project need to be aware of. Plus, the longer time between touching a project that passes means we're more likely to forget. We can add simulation data, mass properties, dimensions, interference detection, measurements, proximity, and costing data, all as a sensor. In this case, I'll simply select a reference dimension, and then I can add an alert that will warn me if my dimension goes below a specific value. We can do that with model dimensions, or even reference dimensions as well. We can also add sensors just by right-clicking on the folder as well. And if I want to see my notifications trigger warnings, those are available as a right-click away as well. Now I get a call from the field, and I hear these tabs are deflecting a bit. So maybe if we beef them up, that'll take care of the problem. So we'll adjust that, and phew, crisis averted, right? But when I go back over to my assembly, we see the warning. So at least I was warned about this, so I know I need to improve my stiffness, but if I go to that value, it's still going to cause issues at manufacturing. So I think I should probably back off that dimension a little bit. And then when I go back to my assembly and rebuild everything, my sensor flag's cleared and we're all set. So what do sensors actually do to our model? Nothing. But we can set ourselves up to remember important details by monitoring specific properties. And we can do this for a variety of design data. So why should we care about assembly visualization? Well, maybe our team is very visual and a chart isn't going to help them understand as much as maybe a model representation would. Or management has tasked us with reducing our design's weight by, 100 pounds or something. So when I launch assembly visualization, the default display is an alphabetically sorted list of our parts with their quantities and mass. We can sort by any of these header columns like mass, and now we've listed them all with mass as being the heaviest at the top. And there's even a rollback bar to hide small components, so that's not part of this visualization. Because I don't want to show the team all of those. And mass isn't the only property we can look at. We can bring in other physical properties, or file properties, or even performance properties like maybe graphics triangles. Now for this review, I want to get the best bang for my buck. So I need to be sure to multiply quantity by the weight. So we can do that inside this custom column with an equation. And now I can see my parts sorted, multiplied through. And once I've got my final look here, dragging my rollback bar up to eliminate some of those parts, we've got a sorted list that I can save out as a display state to go back to show the team. So over my configuration tab, we've got a display state that was filtered out to show the tank's really our main focus. So what does assembly visualization actually do to our model? Nothing. But we can create unique visual representations of our assemblies with specific properties and/or calculations. So why should we care about performance evaluation? I don't know about you guys, but is there anybody that really has too much time on their hands? Well, for the rest of us who don't, rebuild time often feels like wasted time. And what about those times where we know we could benefit from better performance, but we just don't know where to start? So how we tackle that challenge is with performance evaluation. We can get a simple one-click report that shows us all kinds of great data, like a list of parts that are taking a long time to load that we should check out. There's even a list of parts that could be causing issues with high graphics resources. So if you have assembly with a lot of parts, go take a look at this. There's probably a good chance that you've got some parts that have way too many graphics triangles. We also get kind of a stat list of the assembly with how many parts, unique files, and assembly depth as well. All great information for us to understand how does this compare to other assemblies we're used to. There's even a cool one-click button to leverage the last tool we discussed, assembly visualization, which will show all kinds of potential performance issues, like problems with graphics triangles. In our case, one of the worst performing parts is this rot grate, which is actually inside the grill. So what does performance evaluation actually do to our model? Nothing. But it does look at the performance of an assembly and help us with improvement suggestions. And it's super helpful the larger and more complex our assembly is. So why should we care about curvature? Have you ever designed a part you were certain was going to look great, only to see defects when it's finally made? Or how about maybe you're being tasked with getting a more modernized design with smoother blends and transitions? For this grill, the top and bottom covers are what everyone's going to see on the showroom floor. So we want to double check the curvature is consistent and smooth. Rather than going to each individual fillet feature and I can actually see if their curvature continuous, I can see a color representation of these curves. And this design's okay, but I'd really like a version that leverages curvature continuity. And by changing the configuration, we can see there's a gradient of color there, indicating a blended curvature. So how did I get that awesome curvature continuity? Well, if we open up the part file, we can take a look at the curvature continuous option for the profile. So that's going to get me that nice smooth blend all the way around. So what does curvature actually do to our model? Nothing. But it can help us visually see the curvature of our parts within an assembly. So why should we care about symmetry check? Maybe we get complicated parts from suppliers we want to modify. Or we need to be sure to design some asymmetric parts so that we get only single direction assembly. Now I need to make sure that this part can only be assembled one way. So I'm going to check symmetry about the right plane and make sure I have asymmetric parts. SOLIDWORKS shows me no symmetric parts, everything's asymmetric. We can see what parts are asymmetric and even get out a little report. So if I thought I was supposed to have a symmetric part, I can also use that tool as well. Maybe I thought this cap was supposed to be symmetric for whatever reason. So if I open it up at a part level, I can use that tool as well. And at a part level, when I run the symmetric check, symmetry check, I get a listing of unique faces, symmetric faces, and asymmetric faces. And if I look to the inside of this, I can see the obvious reason why those faces are asymmetric about that right plane. So what does symmetry check actually do to the model? Nothing. But we can check for symmetry in parts about a plane, and we can identify unique faces as well. A little side note too, just to be sure, is that it works with the current configuration. So moving along here, why should we care about compare documents? I'm sure none of you have customers that send part revisions that have only text changes, and the geometry is exactly the same, right? In fact, they're actually really different, even though they said that it wasn't. Or maybe we have two parts in inventory that we think are pretty much identical, but you need to be sure. So how I solve that challenge is with compare documents. I choose what my reference document is and what my modified document is. I can do this for parts, assemblies, and drawings. And I can compare properties as well as geometry. So here I've selected my reference document and a modified version that I was told was pretty much the same. And I'm going to check the geometry. When I look at the comparison, SOLIDWORKS tells me I can't do a face comparison because this is an assembly, but I do get a lot of good details out. And I can look at an awesome representation of where the geometry is actually different with these cool different filters. You can see common values or common volumes, materials to add or remove. So that material is different. Obviously, this has been pushed out some. And I can filter down to see that even though maybe when I first opened these parts, they looked pretty much the same, they're not quite the same. So what does compare documents actually do to our model? Nothing. But we can compare document properties, features, geometry, bills of materials for two different configurations of the same document or different documents as well. So why should we care about Simulation Express? How about if we want peace of mind for first pass stress analysis? Or if we have a design idea, but we're not sure if it's going down that path is really worthwhile. Or maybe we want to vet out some of the lower level design ideas before we submit it up the chain to some of our sim experts. And I'm sure none of you guys are ever asked to decrease prototype costs, right? SimExpress is at a part level. Even though it shows up on the Evaluate tab in Assemblies, you really want to only use it for parts. But I'm going to go ahead and show you guys how it works anyway. When we launch SimExpress, we get a nice little handy wizard over here. And it's a step-by-step wizard that walks us through the setup to set up a basic linear part simulation. All we have to do is select fixed faces. And over on the Property Manager, all the boxes should look and feel like traditional SOLIDWORKS dialog boxes that we're used to. So this thing is really intuitive. And I select Next from the task pane, and then I'm ready to add my force. I can select the face and can control the direction of the force and the magnitude. Then SOLIDWORKS will even pull in any material that's already been assigned to the part, or I can change it if I want. And then I can run my simulation, and I get an awesome animation preview showing the distortion of my part, because nothing's worse than drawing conclusions on an incorrect setup. That quick animation made me feel confident I've set this thing up right. It's distorting how I'd expect. And since I'm confident my setup's correct, I can look at my results and see a factor of safety plot, von Mises stress, or displacement. Looking at the factor of safety plot has me worried because I'm seeing areas that are below 1, indicating that part's going to likely fail. And to help communicate these concerns up the channel, I can generate a report from a template or an e-drawings file. This way I can send my discoveries to someone on the team who's not using SOLIDWORKS and clearly communicate what I saw. At this point, maybe I want to try a few different iterations of the design. That's where I can use the Design Express study. Now I can determine CAD geometry I want to change and what factor I'm going to try and drive to achieve. All this from an interface that I'm comfortable and familiar with. Here I'm going to change the width of that sweep and run through a design optimization. Once the study is complete, I can decide whether to use my original CAD value or accept the changes that have been made. But when I jump back over to the Simulation Express study, I probably want to modify my dimension to a nice round number, which I can do from the graphics interface. And then I can rerun my Simulation Express study with the new value to see what are my results, which they should be above 1. See that distortion the same, so my setup is good. And my lowest factor of safety is above 1, so now I'm comfortable with this design. So what does Simulation Express actually do to our model? Nothing. But we can run through a first pass stress analysis, and we can test in a virtual environment to reduce our number of required field tests. We do have to remember that our analysis is only as good as our setup. And we can only calculate displacement, strains, and stresses for linear materials in part files only. So why should we care about Flow Express? Customers may have application requirements that we have to agree to meet. Or maybe, we know our product's great, but we need to create a visual representation that others can easily understand, maybe somebody in marketing. So just like the Sim Express wizard, the Flow Express wizard is a step-by-step guide for us to do quick flow analysis. The first step I didn't show was actually capping the ends. We do need an enclosed volume for this to work. When I select Next, though, I'll see that we've got the volume enclosed. Then I can select what fluid we want, which can be water or air. And then I set my mass flow rate at the inlet. Simply right-selecting and select other, I can pick to the face where that inlet's going to be and what's that mass flow rate. And doing the same for our outlet face. Simply right-click, select other, and then pick through to get the cap on the end. And then Flow Express solves giving me awesome graphics of the fluid flow. There's even these cool animations. So we've got these little piping goes through, and it shows an example of what a particle going through would look like. Maybe we want to use these balls, which might be easier to see. And we can grab images, videos, or generate a report. So what does Flow Express actually do to our model? Nothing. But we can calculate fluid velocities through a single cavity for a single fluid. And just like any simulation, it's only as good as our setup. And we can get all kinds of awesome visual content, including animations. So those could be used for analysis purposes from an engineering perspective, or just for marketing purposes to help show off our product. So why should we care about DriveWorks Express? I'm sure we all love our salespeople, and they keep us in business with new jobs. But I think we all can relate to the salesperson who brings us jobs that are exactly like the one job we just did, only 5 things are different. Or maybe we've got an intern that we want to help have us make some prints. But that intern doesn't know if we choose a 10-foot for part A that we can't use a 10-foot for part B. So how we tackle this type of challenge is with DriveWorks Express. Once we've created our database file, we can go to work. We select what parts we want to use from our open assembly. So we'll use our assembly and our part files, along with any dimensions that we want to add to our project. We can even give the dimensions names that we want to use for our iteration process. And this will make it nice and clear what dimensions we're changing in our forms. We can choose to include specific features as well, like maybe this diagonal support's an optional feature for super strong systems. We can even determine what already created specific custom properties we want to pull in from our models. I don't know about you guys, but I hate creating drawings over and over again. So we can decide what drawings are the starting point for our future projects. Now, I'll probably have some finished work to do on those, but at least I won't have to start from scratch. We can also determine if we want to allow configurations to be generated within the model itself, or just generate a new model. Then we simply create input fields that are going to be used on our form. We can control what type of input the user can put in, like text. So in this case, project number is going to be a text box. We can do limited ranges. Or even pick from a drop-down list. Maybe there are specific inputs that are only available. So we want to say, maybe we've got several different options for different weights, but we can't do all of them. Basically, we create anything we want to ensure we don't accidentally create an impossible design. With the form set, all we have to do is build up our logic, which is where the real power of DriveWorks Express shines. We spec out any of the new files that were going to be created, configurations, custom properties, dimensions, and features that all need some level of logic to help generate those values. And they can be as simple as use the value from the form to more complicated math and logical operations here where we're at using ands and space, using other math operations as well. So basically, this logic creates the end output information. Now to create a new version of this system, all we have to do is input the information in our form, and DriveWorks takes care of the rest. It uses our built-up logic to create new parts, assemblies, and drawings as necessary. And it really cuts down on the time we have to spend coming up with these designs that are exactly like the one we just did, only different. So we generated a whole new set of assembly documents and part files and drawing files just by filling out the form. Now we don't have to worry about our intern. He can go to work. So what does DriveWorks actually do to our model? Nothing. But we can create a master model that can create other files. So why should we care about costing? Well, if we have a manual costing process, or the thumb in the air style process as I like to call it, maybe we've got some of our veterans that are retiring, and we've got some other folks with less experience that really don't have a good feel for our costs. Or maybe we're looking to use some different machines for a short term and aren't sure how that's going to impact our cost. How we solve that is with costing. Assembly level costing helps us finish out a costing job based on what still needs to be calculated, along with parts and assemblies that already have calculated costs. So these come from other SOLIDWORKS calculations. And we can use purchased parts costs or built-in toolbox item costs. So that's pulling in data. Then simply begin the costing estimation for the missing parts of the puzzle. Any parts whose costs are already calculated by SOLIDWORKS costing are in a separate folder, so we can see those. So those were calculated during this run. Any purchased parts are separated out as well, along with a separate folder for toolbox items as well. And if we've got any assembly level costs, we can have those built in as well. Now, the real secret sauce to this whole process is our template editor. The template editor allows us to add assembly level feature costs and logic into our costing model based on our own data. Costing can really be thought of as just really another simulation. And so as with any other simulation, the output's only as good as the information going in. So to use this tool, we really need to take some time to input our own data, because the default data is really just for demonstration purposes. It's not real costs. And when we're happy with our cost information, we can output a report, either for internal review or maybe to quote for a specific customer. And we can get as detailed as we want with these reviews. This detailed cost report is really great for internal reviews so that we can see how the costs all break down. And now it should be noted, we really shouldn't be running our accounting software based on these cost breakdowns or making dramatic changes to our business model on these cost reports, but they do give us insight into that directional level change for new ideas and modifications. So what does costing actually do to our model? Nothing. But we can automate the costing process for sheet metal, machined, multi-body parts, assemblies, plastic molded parts, cast, 3D printed parts, and multi-body weldments as well. And most importantly, these costs are a guide, and they're really only accurate as our setup. So why should we care about sustainability? Maybe our company's got green initiatives, or one of our core values is reducing carbon footprint. Or maybe our own personal conscience is worried about our future. So how we solve this challenge is with sustainability. We can select the class of material we're using, locations, and see an environmental impact report based on our part. Then when we decide we're going to change our material, we can see what the impact that will have, up or down or by what percent. And similarly, we can see what impact we'll have if we bring manufacturing back here from overseas, maybe, for example. So currently, maybe this part's made overseas, and we want to see what it would be like if we brought it back to the States. So we can use this data to help us make informed decisions and see the bigger picture. Just that we're saving 3 cents by sending it overseas might not be enough. We can help our team understand what the real cost is based on our green initiatives. And once we have our settings based on how we produce today, we can always set the baseline to compare any new ideas against. Without setting a baseline, every change is shown against the previous iteration. With the baseline set, we're always comparing against the same setup. Maybe we're trying to find new alternatives, but we're really not sure what would be a good fit. We can find similar materials that match design criteria we set. From a fit, form, function standpoint, I love this capability because we're able to narrow down what's important to us and find alternative solutions that we may never have thought to consider. We are going to have to do a little bit more digging to verify, true cost data on, big material changes, but to find if it's comparable. But we could find, potential for a better material that's got better impact. We can even compare different manufacturing methods, like materials, to see if those have different impacts as well. And since all this work's done inside of SOLIDWORKS, we can use familiar tools to edit the material of the part once we've made our selection. So from that task pane, we see set material, which looks just like it does over on the task pane in our design tree. At this point, we'd probably be ready to make the suggestion up the chain to further evaluate this switch. And what's cool is we can get some insight on the material cost impact. So we do see some level of information on that. So we don't propose a crazy change. And I wouldn't go down to the penny level on cost with this tool, but for the material financial impact, it does help, though, for us to understand we're in the ballpark of comparable costs. So what does the sustainability tool actually do to our model? Nothing. But we can understand how different decisions impact our carbon footprint. So whenever we're creating assemblies, let's always remember Simon's circle and start by focusing on the why. Why are we creating the assemblies in the first place? Because the evaluation tools are how we answer those questions. But even though what those tools actually do to our model is nothing, the insight they provide means everything. So at this point, I'd like to go ahead and hand it back over to Chris.
Excellent. Thank you very much, Brandon. I never realized I could learn so much about my model by doing absolutely nothing to it. Kind of an interesting perspective on that. Thank you, everyone, for joining us today. Thank you so much, Brandon, for the presentation, for enlightening everyone on all the great tools on the Evaluate toolbar. As we wrap up, we'll just talk about a few webcasts we have finishing out May through June. So we have our hardware webcast on May 28th about the Desktop Metal Studio Plus system. June 13th, discussing SOLIDWORKS inspection and faster ways to create the inspection documentation. Scanning presentation with the Cube R in June, and then wrapping up June, the SOLIDWORKS Catapult Hero to Zero about advanced surfacing. So with that said, thank you again so much for everyone joining. Everyone have a great day, and hope to see you again soon on one of our future webcasts.